Welcome. All right, so last time we were talking about Jacobi iteration. Today we're going to talk about eigenvalues and eigenvectors. Okay, so this is some very important mathematical machinery that we're going to use over and over and over again in future lectures. Okay, so eigenvalues and eigenvectors. So remember, linear algebra is not a prerequisite for this class, but we are going to use linear algebra, okay? So if you haven't seen this before, we're going to go through all of the stuff you need to work with eigenvalues and eigenvectors. But remember, linear algebra is not a prerequisite, okay? So eigen is this great German word that means latent or characteristic. Characteristic. Okay, and in some sense, these are special values and special vectors that pop out of a matrix A. Okay, so we've been looking at a matrix set of equations x k plus 1 equals a matrix A times x at index k. Right, so this is some vector, we multiply it by A, and we get a vector at a future instant or a future iteration. So for example, this could be the Jacobi iteration we saw. And sometimes xk blows up, meaning it goes to infinity. Okay, sometimes it blows up, which means it goes to infinity, and sometimes xk decays, which means it goes to 0, right? So in the case of a Jacobi iteration, if this is the error equation, remember we had error k plus 1 equals minus d, the diagonal part, inverse times t, which was everything else in A. Epsilon k. We want epsilon k plus 1 to go to 0. We want our error to go to 0, which means our iteration is working, okay? So why does it sometimes blow up and why does it sometimes decay? So the answer to this question is hidden in the eigenvalues of A. Okay? So I'm going to tell you what the eigenvalues and eigenvectors are. I'm going to start by showing you an equation that they satisfy, and then we're going to get some feeling for what they are by working through an example. Okay, so the really important equation is AX equals lambda x. Okay, this is so important that I'm going to put a box around it. Okay. So this is not true for all vectors x and all numbers lambda. This is only true for special. This is true for what I'm going to call special x, which are vectors, and special lambda, which are numbers. Okay, so lambda and x that satisfy this equation are my eigenvalues. Lambda would be my eigenvalue, and x would be my eigenvector. Okay, so not all lambda and x satisfy this equation, but those values and vectors that satisfy this are called eigenvalues and eigenvectors. Okay, so I'm just telling you that this is a very important set of numbers lambda and vectors x, and we'll see why they're important in a few minutes, okay? But before we dive into more theory, let's just get a feeling for what this equation looks like, okay? So we're going to start with an example. We're going to say, okay, let's say my A matrix is 3, minus 1, minus 1, 3, okay? And we're going to see what vectors satisfy my eigenvalue equation. So first we're going to try this vector, x equals 1, 0. Okay, so what is a times x? Okay, a times x equals, well, I multiply, I get 3 on the top, 3 plus 0, and then I multiply and I get minus 1. Okay, so ax does not equal some number times x, right? There's no lambda times x that would give me this. They're pointing in different directions. In fact, let's plot these. Okay, so what we're going to do is we're going to plot the vector x and the vector ax here. Let's see. Okay, so what I'm going to do, I'm just going to use different colors for each of these. So the first vector I tried is 1 in the first coordinate and 0 in the second coordinate. So this is my first vector x. And a times x is 3 minus 1. So I go 1, 2, 3, and down 1. Okay, so this is ax. And they do not point in the same direction, right? They're pointing in different directions. All right, let's try a different vector. Let's try x equals 0, 1. Okay, so now instead of going 1 in this direction, we're going to go 1 in the vertical direction. I'm going to use a different color for that. Okay, so we're going to try another vector. So first, the green vector was 1, 0 here. Now we're going to try 0, 1. Okay, that's a vertical vector, 0, 1. And what is a times this x? Well, if I multiply 0, 1, I get negative 1. And 0, 1, I get a positive 3. So now I go left 1 and down 3. Okay, again, these vectors do not point in the same direction. And so there's no number lambda such that lambda times x equals ax. Okay? But let's try a different value. I'm going to call this my special x. Let's try the special value x equals 1, 1. Okay? So if I look at a times x, I get 3 minus 1 is 2. And minus 1 plus 3 is also 2. Now this is interesting. So these vectors are actually pointing in the same direction, right? If I plot my original x, its coordinates are 1, 1. And a times x have coordinates 2, 2, which means I go over 2 and up 2. So x and ax. Okay, so they point in the same direction, and this means that x is actually an eigenvector of a, right? So 2 times x equals a times x. Okay, so my eigenvalue is 2, and my eigenvector is x with coordinates 1, 1. Okay, so this is what an eigenvalue and eigenvector mean. Out of all of the directions I can choose my vectors x, most of them map to a different direction when I multiply with a, but my special eigenvectors x map to the very same direction. So all I have to do is scale them by this number lambda. Okay? Now there's another special eigenvalue and eigenvector. So let's try the second one. Let's try x equals 1 minus 1. Okay, and this maps to a times x equals, okay, so 1 times 3 plus minus 1 times minus 1 is 4. And similarly, 1 times minus 1 is minus 1, plus -1 times 3 is -4. Okay, so let's plot these vectors in red. Okay, so my first vector, I go to the right 1 and down 1. This is x. And then when I map through A, I go to the right 4 and down 4. 1, 2, 3, 4, 1, 2, 3, 4, which is in the same direction. Okay, so x equals 1 minus 1 is also an eigenvector of the matrix A with eigenvalue lambda equals 4. Okay, so 4 times x equals A times x. Okay, so what this means is that the matrix A, most directions x are not eigenvectors, but some special directions are, and what that means is that they map to the same direction, and all we have to do is scale by the eigenvalue lambda. Okay? Okay, great. So this gives us a geometric feeling for what these special vectors and special values mean. And now we're going to go back and see how we would calculate them. So I basically was just trying vectors until I stumbled upon my special eigenvectors. But we really would like to know, how do we determine these without just guessing? Okay, so that's what we're going to do now. All right, so let's keep our equation. Okay, so the equation that we want is ax equals lambda x, right? So this is the equation. We want to find numbers lambda and vectors x that satisfy this equation, okay? Now, lambda, a number times a vector x, is the same as writing lambda times the identity matrix times the vector x, right? Because identity matrix times x is just x. So this is the same equation. And I'm going to move this lambda identity x to the left-hand side. So what I get is A minus lambda times the identity times my vector x equals 0. Okay? Pretty simple so far. So this is exactly the same as this. So lambda and x that satisfy this top equation will also satisfy this bottom equation. And there are two cases. Okay? So case 1 would be that my vector x is equal to 0, right? That certainly solves this equation. If x is 0, then whatever I multiply it by still gives me 0. But this is, in some sense, not interesting. This is kind of a boring solution, right? This is certainly a solution, but it's not the one we're looking for. Now, case 2 is that x is not equal to 0, and the determinant of a minus lambda I equals 0. Okay? So if I want a non-zero eigenvector solution, then what needs to happen is that the determinant of a minus lambda I has to equal 0. Okay? Now this is a mathematical property that I'm not going to verify. I'm not going to prove to you why this has to be true to get a non-zero eigenvector x. This is just an unverified fact. And getting to the bottom of this is really the subject of a class in linear algebra. Okay? If this is true, though, I guarantee you that I will be able to find non-zero eigenvectors x. And what we say is that a minus lambda I is singular. Okay, this is just mathematical jargon. When the determinant of a minus lambda I is 0, we say that that matrix a minus lambda I is singular. Okay? And so the determinant of a minus lambda I equal to 0. This is a polynomial equation. This is what we want. We want to find lambda such that this determinant does in fact equal 0, because that's when I'm guaranteed to have non-trivial eigenvectors. Okay, so this determinant of a minus lambda I equal to 0 is a polynomial equation, and the roots lambda are eigenvalues. Okay? This is called the characteristic equation. And so it's no surprise that in German, characteristic values are eigenvalues. Okay? So this is the equation we need to solve if we want to find eigenvalues lambda. Okay? So this is, we're just going to work this out on the example from before. Okay, so in our example from before, we have a equals 3 minus 1 minus 1, 3. Okay, and we're going to compute the eigenvalues of this thing using the formula that we just derived. Okay. All right, so let's just remember what we're trying to solve. We're going to look at the determinant of a minus lambda I equal to 0. That's what we're going to try to solve lambda such that this is true. So let's look at a minus lambda I. A minus lambda I equals, okay, lambda times the identity. This is 3 minus 1 minus 1, 3 minus lambda 0, 0, lambda, right? This is lambda times the identity. And this equals 3 minus lambda minus 1 minus 1, 3 minus lambda. Okay, not so bad so far. So now what we're going to do is compute the determinant of this thing. Okay, let's look at that. So the determinant of a minus lambda I. Now remember, if I want to compute the determinant of a 2 by 2 matrix, what I do is I multiply the diagonal terms, and then I subtract the product of the off-diagonal terms. Okay, so this is equal to 3 minus lambda times 3 minus lambda minus negative 1 times negative 1, which is positive 1, minus 1. Okay, that's pretty straightforward. So this equals lambda squared minus 6 lambda plus 9 minus 1. Okay, all I did was expand this out and then subtract 1. So this is equal to lambda squared minus 6 lambda plus 8. Okay. And what we end up getting is, remember this is supposed to equal 0. So this is lambda minus 4 times lambda minus 2 equals 0. So for what values of lambda does this equation equal 0? Right? When lambda equals 4 and lambda equals 2. So lambda equals 2 and lambda equals 4 are solutions to the determinant of a minus lambda I equals 0, and they are eigenvalues. Okay, so this is how we do it for an example. If I have a matrix A, I look at a minus lambda I, pretty simple. I compute the determinant of that matrix. I get a polynomial in lambda. I set that polynomial equal to 0, and I solve for lambda, right? I get lambda equals 2 and lambda equals 4. Those are the values we got earlier when we guessed our special eigenvectors. Okay? Now, just a fact that might be helpful for you, just the generic formula for the determinant of a 2 by 2 matrix. B, let's say I have a matrix B, and it equals B11, B12, B21, B22, okay, then the determinant of B, right, so this is B, the determinant of B is going to equal B11, B22, minus B12, B21. Okay, so I'm not going to expect you to know how to compute the determinant of a 5 by 5 or 6 by 6 matrix, but you might actually want to know how to compute the determinant of a 2 by 2 matrix because you might want to be able to compute the eigenvalues on pencil and paper like this. Okay, so this is pretty useful. And the same procedure follows if I have a 3 by 3 or a 4 by 4 matrix. I just compute the determinant of that larger A minus lambda I. Okay? Okay, great. So now what we want to do is now that we have our eigenvalues lambda equals 2 and lambda equals 4, the second step, so this is kind of step 1. Step 1, compute lambda. The second step is going to be to compute my eigenvectors once I have lambda, okay? All right. And once I have lambda, it's pretty simple. I could, right, so step 2, get x given lambda. Okay. Right, so our system of equations is ax equals lambda x. And we're going to say this is really a minus lambda I, x equals 0. And we're just going to plug in lambda and solve for x. Okay? Solve for x. So let's try this for our system of equations before. Let's just write this up so we remember. A equals 3 minus 1 minus 1, 3. And we know that one of our eigenvalues is lambda equals 2. So I'm going to plug this in and solve for x. What is a minus 2 times the identity? Okay, well, this matrix A minus 2, 2 on the diagonal is equal to 1 minus 1 minus 1, 1. Okay, so this matrix, 1 minus 1 minus 1, 1, we're going to solve for x. Okay, this matrix, A minus 2i times x equals 0. Okay? So what we get is that x1 minus x2 has to equal 0, and minus x1 plus x2 has to equal 0. Well, both of these equations are satisfied as long as x1 equals equals positive x2. Right? As long as x1 equals x2, both of these equations are satisfied. So x equals a vector 1, 1 is an eigenvector. Now, interestingly enough, if I plug in x1 equals 2, so x equals 2, 2 is also an eigenvector. So in fact, anything in this direction will be considered an eigenvector, but we really call them, they're kind of all in the same direction, and so we call that one eigenvector direction. Okay, good. And we can just verify that this actually does satisfy our equation. So if we look at a times x, so what is a times x? That's equal to 3 minus 1 is 2, and minus 1 plus 3 is 2. This does, in fact, equal lambda times x, right? So this does satisfy our eigenvalue equation. Okay, let's do the same thing for our lambda equals 4 eigenvalue. And the procedure is almost identical, okay? So we're basically just doing this for practice, okay? So we know that our other eigenvalue is lambda equals 4. So what we're going to do is plug in a minus 4 times the identity. So what is that? That's just equal to minus 1, minus 1, minus 1, minus 1. And again, we want to solve the system of equations minus 1, minus 1, minus 1, minus 1 times x equals 0. And so we get the kind of identical equations that x1 minus x1 minus x2 equals 0, and this means x1 has to equal minus x2. Okay? So this solution is x equals 1 minus 1 satisfies this system of equations. And so this is another eigenvector. And we say that it's the eigenvector corresponding to the eigenvalue lambda equals 4. Okay, so these things come in pairs. I had two eigenvalues, lambda equals 2 and lambda equals 4, and each of those eigenvalues had their own eigenvector direction, okay? And this is how you compute them. So it's a two-step process. First I compute lambda, and then I compute x, okay? Now, what we can do right off the bat is, if we go to MATLAB, let's see, all right. So I'm just going to show you, this is how you do it by hand, but MATLAB has some really nice built-in techniques to compute these eigenvalues, okay? So I'm going to clear everything, and I'm just going to enter a matrix A equals 3 minus 1 minus 1, 3, which I believe is what we are working with. Okay, good, that's my A matrix. So now if I say eig of A, it should spit out the eigenvalues of A, hopefully. Good, and the answer is 2 and 4. Those are my eigenvalues of the matrix A, and that's what I expect, okay? Now if I say, let's do help eig. So there's actually, in most MATLAB functions, there are ways of getting different types of outputs. So if I just say eig of A, it just gives me the eigenvalues. But here, if I say V comma D equals eig, then I will get two outputs, a matrix V and a matrix D. Okay, so I'm going to say T comma D equals eig of A. And now what it gives me is two matrices T and D. D is a matrix which has diagonal elements, which are my eigenvalues, right? D equals a matrix with 2 and 4 on the diagonal. And T is a matrix of eigenvectors. Okay, so the columns of T are eigenvectors. Now notice that it looks a little different than the eigenvectors we computed, right? We had 1, 1, and 1 minus 1. What it's done is essentially scaled them so that they have unit length, right? So if you take our vector 1, 1, and you divide by the square root of 2, so that it has unit length, you get their value, right? 1 over square root of 2 is 0.707. So MATLAB is going to give you a matrix T of normalized eigenvectors and a matrix D, which is diagonal with entries given by the eigenvalues. Now, why is this useful? I'll tell you a really interesting fact that I use over and over again kind of all throughout numerical mathematics is this fact. So this is really useful for telling if your iteration is stable. It's also really useful for looking at differential equations and many other things. So MATLAB gives you this output t comma d equals eig of a. Okay, this is literally something I can type into MATLAB. Okay, this is a MATLAB equation. T is a matrix of eigenvectors. So these are my E-vecs. And D is a diagonal matrix of eigenvalues. And there's a really interesting property that these matrices satisfy. So these satisfy A equals T times D times T inverse. Okay, now this is a very important equation, so I'm going to box it, okay? So A equals T times D times T inverse. This will always be true for the matrices T and D that are the eigenvectors and eigenvalues that are spit out of MATLAB. Remember, T is a matrix of eigenvectors. So the columns of T are eigenvectors, x corresponding to my first eigenvalue, my second eigenvalue, and so on. And D is a diagonal matrix of said eigenvalues. Everything else is 0. Okay, now the really nice thing about this is that, well, there's a few nice things about this. So I can compute D to a power n very easily. Right? It's hard for me to compute A to the power n because matrix multiplication is expensive. But multiplying a diagonal matrix by itself is actually very cheap. All I have to do is multiply the diagonal elements. So this equals lambda 1 to the n, lambda 2 to the n, and then my last eigenvalue to the n. Very cheap, okay? And what we find is if I want to compute A to a power, right? So in my Jacobi iteration, I keep multiplying by A over and over and over and over again. So I'm really concerned with this matrix A to the power n. This equals T times D times T inverse times T times D times T inverse times the same thing n times, right? I just take n copies of A, and A equals T times D times T inverse, and I multiply it that many times. Now what's great is that all of these T inverse times T in the middle cancel out. These all become the identity, and all that I'm left with is T times D to the power n times T inverse, okay? So this is a much, much more efficient way of computing A to the power n than actually multiplying this matrix A a bunch of times, right? It's easy to compute D to the n. And so this is a very, very useful formula, okay? Now just the last point that I think is really interesting here. Remember, A to the n equals T D to the n T inverse. This matrix is going to get very, very large. So this is going to be, so we have these lambda to the power n's. That's what D is made, a diagonal matrix with entries lambda to the n. This is tiny if lambda is less than 1. It's huge if lambda is greater than 1, and it's equal to 1 if lambda is equal to 1. Okay, so this is another interesting fact, is that if I have a matrix A that I'm applying over and over and over again, so I'm looking at A to the power n, this matrix is either going to be very large or very small, depending on the eigenvalues of the matrix. Okay, so if my eigenvalues are less than 1, then everything is shrinking. In some sense, my error might be converging in the case of Jacobi iteration. if my eigenvalue is greater than 1, then everything is getting bigger and bigger inside of this matrix A to the n. Okay? And for example, I can take, remember we have this equation lambda x equals ax. This is true for eigenvectors x and eigenvalues. So let's say I look at my equation xk plus 1 equals a times xk. And I start with my first x is an eigenvector. Okay, so if x1 is an eigenvector and I multiply it by a, that's the same as multiplying it by lambda. So this goes to lambda x1. Now, right, so this is x2 equals lambda times x1. Okay, that's what this map is saying. If I apply my map A again, my matrix multiplication A again, x2 is still in the eigenvector direction, so I multiply it by another lambda. Okay, so x3 equals lambda squared times x1. x4 equals lambda cubed times x1, and so on, so that my x, after n iterations, is equal to lambda to the big N minus 1 times x1. So basically, if I start in an eigenvector direction, x1, and my eigenvalue is less than 1, then x is going to converge to 0, because lambda to the big number is really small, right? Let's say lambda is 0.1, and n is 1,000. Right, so 0.1 to the 1,000th power is a very, very tiny number, and xn is almost exactly 0. Similarly, if lambda is a big number, let's say lambda is 10, then lambda to a big power is astronomically large. Okay, so this is why eigenvalues and eigenvectors are important, because they tell you something about kind of how iterations through this matrix multiplication A either get very large or very small. Okay, now I'm not telling you all of the story, right? So here we just said this lambda to the power n is tiny if lambda is less than 1, it's huge if lambda is greater than 1, and it's equal to 1 if lambda is equal to 1. But if you were kind of comfortable with these determinants and linear algebra, you'll probably remember that I can actually get eigenvalues and eigenvectors, which are complex numbers, okay? So the story is a little more complex than what I just told you. So let's look at an example of that, okay? So if I have this matrix A equals 0, 2, minus 8, 0. Remember how we compute eigenvalues. We solve this equation. We look at the determinant of A minus lambda I, and we set it equal to 0. Okay, so A minus lambda I is minus lambda to minus 8 minus lambda, and the determinant of this equals lambda squared plus 8, and we want that to equal 0. Okay, so we get lambda squared equals minus 8. I think I did something wrong. This is minus 8 times 2. So my determinant's plus 16. Okay, and lambda equals plus or minus 4i. Okay, so I can certainly have complex eigenvalues. In this case, lambda equals plus or minus 4i. And so all of the things I said about this lambda to the power n change a little bit for complex numbers, okay? So let's look at that. Okay, so instead of lambda 1 being less than 1, what we're going to look at is where lambda is in the complex plane. Right, so I have the complex plane, I have lambda equals some real number plus some imaginary number, right? It's a real number plus an imaginary number. And now what I'm going to look at is whether or not lambda, so lambda can be inside this unit circle so that the length of my lambda vector is less than 1, or lambda can be outside the unit circle so that the length of lambda is greater than 1. Okay, so all of the theory carries over now. Lambda to the power n will still be tiny, but now we require that the absolute value of lambda is less than 1, where the absolute value of lambda is it's the length of the vector in the complex plane. Okay, so the length of lambda is equal to the square root of x squared plus y squared, right? So if this number is small, then multiplying it multiple times is going to get something smaller and smaller and smaller. So this is how it generalizes to complex eigenvalues, okay? Let's see. We can also write this in polar coordinates. So instead of lambda equals x plus iy, we can say lambda equals coordinates r and theta. So for example, let's say this is my vector lambda. Okay, so it has some angle theta, and it has a radius r. And this is the length of my vector is what I'm calling r. Now there's a rule in complex arithmetic that lambda squared is equal to r squared with an angle of 2 theta, right? So if I take lambda and square it, then my radius becomes my radius squared, and I increase my angle by another theta. Okay, and I keep going down, and I get lambda to the power n equals r to the n with an angle of n theta. And so notice that the magnitude of this complex number, lambda to the power n, is given by r to the power n, right? So absolute value of lambda is r. The magnitude of this is going to be tiny if r is less than 1, right? Because something less than 1 taken to a very large power goes to 0. And it's going to be huge if my radius is greater than 1. Okay, so this essentially tells us how a system xk plus 1 equals a times xk will behave. So if I want this solution xk plus 1 to go to 0, then I require all of its eigenvalues to be within the unit circle. All of its eigenvalues have to be inside this unit circle for this system to be stable, meaning that it iterates to something closer and closer to 0. And if any of the eigenvalues are outside the unit circle, then there are x values that will blow up to infinity. Okay? So that's all for this lecture. And in the next lecture, what we're going to do is combine the ideas of eigenvalues and eigenvectors with the Jacobi iteration that we saw in the previous lecture. All right, thank you.